Welcome to 6-8 video lesson underneath Algebra 2. There are 10 boxes for us to talk about, and the concept is one-to-one functions and graphing radicals. So one-to-one functions and graphing radicals. Okay, so let's talk about one-to-one functions. On the left-hand side, I have the function in red graphed for you, f of x equals x squared. And that should just be like the standard parabola. That's not really anything new to anybody that we have introduced so far. The idea here is that the x squared function is indeed a function because it passes the vertical line test like I just shown for you there. But it does not pass what's known as the horizontal line test. Because if I draw a line, then I have two places where my line would intersect my graph. That tells me that the function's inverse is not a function. So take a look down here. If I graph the inverse of the function of the parabola of x squared, I would get the square root of x. And since I take the plus and the minus square root of x, when I tried the vertical line test on this one, it does not pass, it fails. So this tells me that I don't have an inverse that is also a function. I can draw the inverse, but the inverse is not a function. So what do? In order to make something one-to-one, the function itself must be a function, and it must have an inverse that's also a function as well. So in order to make x squared a one-to-one function, we're gonna restrict the domain for values that are strictly greater than or equal to 0. So check this out. If I have this red graph here, I'm only gonna graph these points right here for x's that are greater than or equal to 0. Therefore, when I would graph the inverse function, I would only have this graph, the square root of x, where x is greater than or equal to 0. And this is now one-to-one because the function itself is a function and its inverse is also a function, meaning that the function itself would pass both the vertical and the horizontal line test. So that's what it means to be a one-to-one function. Okay, box 2, I'm going to show you an example of a one-to-one function algebraically. So I'm going to show you that f of x and f inverse of x are inverses of each other, and this is going to tell me that I have a one-to-one function. So here's what I want to do. I want to show that f of f inverse of x is equal to x. So what does that mean? That means I want f of f inverse of x. So I get to use function composition here. So this is going to tell me that I want f of f inverse of x is defined as this piece right here, x minus 1 over 3. So I'm going to say this is going to be, I want f of x minus 1 over 3. So that means I'm going to take this and I'm going to substitute it right there for my x value. So I'm going to have 3 over x minus 1 over 3 and then a plus 1. So 3 times all this stuff cancels out. That leaves me with x minus 1 plus 1, and that gives me x, and that's what I wanted to show. I wanted to show that f inverse of x gives me back x. In addition, I also want to show that f inverse of f of x also gives me back x. So that means I want f inverse of f of x, which is right here, 3x plus 1. I want to show that this is indeed equal to x. So I'm going to take this stuff and plug it right there. So here's what I would get. I would get 3x plus 1, then minus 1, all divided by 3. And I want to show that this is equal to x. So 3x plus 1 minus 1 gives me 3x divided by 3. 3's cancel, and I get that x is equal to x, which is what I wanted to show right here. Sorry. So in order to show that a function is one-to-one, you have to show that f of f inverse of x equals x and f inverse of f of x equals x. Okay, for box number 3, I'm going to show you the basic radical function, the graph of f of x equals the square root of x. I've got some points here graphed for you, so all I did was I plugged them in. So if I plug in 0, the square root of 0 is 0. Oh, sorry guys. The square root of 0 is 0. The square root of 1 is 1. Square root of 4 is 2, and the square root of 9 is 3. So if I start to plot these points, I would get 0, 0, 1, 1, 4, 2, and then way over here I'd have 9, 3. So I'd have this graph that looks something like this. I call this graph kind of the shark fin graph because if I was to do like that and go like this, it would make it look like a shark fin. But the important piece of information here is to know that the domain of this function here, anything that's underneath the radical has to be greater than or equal to 0 because I'm not allowed to take negative square roots of numbers in the real number system. So we want to make sure that we understand the domain and of course the range. If I look at all the y values is also y is greater than or equal to 0. So we want to make sure we have the domain and the range down for our basic radical function square root of x. Okay, in box 4, we're going to talk about vertical translations of our square root function. So if blue, for example, if I want to take f of x equals the square root of x plus 2, this plus 2 on the back end, is going to move my entire graph up 2 units. So this should look very familiar to you. It works the same way with parabolas. So if I have the basic function graph, if I move it up 2 units, this point would be here, this point would be there, and this point would be here. So I'd have this graph here, and this would be the square root of x and then plus 2. And in green for you, if I want the square root of x and then minus 3, notice that the minus 3 and the plus 2 are outside the radical. That's going to be down 3 units. So I go down 1, 2, 3, down 1, 2, 3, and down 1, 2, 3. So this green graph here would be the square root of x and then a minus 3 outside from the radical. So moving a square root function up or down is pretty standard, just like it was for the parabola. If we just add a number, we go up. If we subtract a number, we go down, as long as that number is outside the square root. Okay, let's talk about horizontal translations here. So just like with the parabola, we can move it up and down, but we can also move it left or right. So take, for example, this blue one. If I have the square root of x plus 3, this plus 3 underneath the radical is going to mean that I'm going to move 3 units to the left. Okay, 3 units to the left. It's counterintuitive because most people think if I'm adding 3, I should go to the right, but it works the same way as the parabola. So we're going to go 3 units to the left. So this is going to be 1, 2, 3 to the left, and then 1, 2, 3 to the left, and then 1, 2, 3 to the left, okay? So that right there, the blue graph, is the square root of an x plus 3. Now the green graph is the square root of x minus 2. That minus 2 underneath the radical means I'm going to go 2 units to the right. So 1, 2, 1, 2, and then 1, 2. So I'd have this graph here, and that green one is the square root of an x and then a minus 2. So it works the same way as parabolas. It is opposite the direction you think it would be if it's underneath the square root for moving left and right. Okay, I want this one to be a U-try in box number 6. Check out this equation. This is a standard square root function, but it has been moved from the center. It has been moved left or right and up or down. So you're going to be having 2 different things here. Try and figure out the equation for this. Hopefully you got the right answer, but here's one way you can think about doing it. If my if my square root function had not moved at all, it would look like this. I'd have 0, 0, I'd have 1, 1, and then I'd have 4, 2. So to get to here, I had to move 3 units to the left and 2 units down. So that would be the square root of an x plus 3. That would give me 3 units to the left, and then minus 2 would give me 2 units down. So the answer is the square root of x plus 3, and then subtracting 2. Okay, box number 7, we can also talk about reflections. If I want to talk about the reflection of the square root of function over the x-axis, if I put a minus sign out in front of my function, it's going to give me a reflection over the x-axis. So it would look like this. Instead of 0, 0, I would have 0, 0. That actually doesn't go anywhere, right? Instead of 1, 1, I'd have 1, negative 1. And instead of 4, 2, I'd have 4, negative 2. So this right here in green would be the negative square root of x, okay? So what if I wanted to then graph, I'll do this one in red for you down here, the negative 2 times the square root of x plus 1. Well, I would start with my regular function, square root of x, plus 1 means I'd go 1 unit to the left. So each of these goes 1 unit to the left. So I'd have this red graph here. Then I would reflect it over. So I'd have this graph here, and this one, oh, sorry, that one there, and this one here, and then this 3 goes here, okay? And then finally, that 2 means I'm going to stretch each point by a factor of 2. So instead of 0, negative 1, I'd have 0, negative 2. Instead of 3, negative 2, I'd have 3, negative 4. So I'd have 2 times the output value for that one. So if I wanted negative 2 times the square root of x plus 1, it would be this graph right there. Okay, in box 8, I'm going to ask you some questions about the function f of x equals negative 5 times the square root of x plus 7, then plus 1. All right, in box number 9, we're going to talk about the cubed root of x. This is a cube root of x. So let's start by exploring and taking a table of values and looking at what kind of picture we get. If I took the cube root of -8, I would get -2, because -2 times -2 times -2 gives me back -8. The cube root of -1 is 1, -1. Cube root of 0 is 0, cube root of 1 is 1, and the cube root of 8 is 2. So if I were to graph this at -8, I would be down here at -2. At -1, I'd be here at 1. At 0, I'd be at 0. 1, I'd be at 1. And at 8, I would be at 2. So this is a really cool shape looking graph here, and it looks something like that. So this is kind of like what I call a backwards or stretched out looking S, right? If I look at that, like the number S, if I stretch out the S, it looks like the cube root function right there. So this is another one that we need to be able to graph, and these are the 5 basic points that we want to use for that. If we talk about the domain of the cube root function, you should see that it is all real numbers, and the range for this thing is also all real numbers, right? I can pick any x value that I want, and I can pick any y value that I want. Okay, and then lastly for box 10, I'm going to show you how to graph f of x equals 2 times the cube root of x plus 1 and then minus 4. So the first thing that I'm going to do is graph the cube root of x. So that's going to be 0, 0, 1, 1, -1, -1, 8, 2, and then -8, -2. So in blue, this would be my graph for the first one here. Then I'll change colors for you. In number 2, I would graph the cube root of, and then an x plus 1. So each dot gets moved 1 unit to the left. So this dot goes here, this dot goes here, this dot goes there, that one goes there, and then this one goes here. So I'd have this graph looking like that, okay? Then in red for you, the third thing I would do is I would multiply this value by 2. So I'd have 2 times the cube root of an x plus 1. Okay, so instead of the output value, -1, 0, that's going to stay there because 0 times 2 is still 0. This is 0, 1. I'm going to double that, so 0, 2. This is 2, -1, so I'm going to double that, 2, -2. This is 7, 2, so I'm going to go 7, 4. And this is -9, -2, so I'm going to go -9, -4. So I'd have this graph going on right here. So it had been vertically stretched by a factor of 2. And then lastly, in black for you, I'll graph the whole thing. So I'm going to take that 2 times the cube root of x plus 1 and then a minus 4. So each dot goes down 4 units. So that dot goes here. 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 3, and then 4. So I would have this graph, which is looking, did I do that one right? 1, 2, 3, 4, that goes here, thanks. So it goes there, and then down, and then out like that. So that's how you would sketch 2 times the cube root of x plus 1, then a minus 4. I like to do it in these iterations for you, to show one step at a time so you understand what each piece is doing. All right, big lesson, but it's our last one for the unit, so congratulations.